Good afternoon, everyone. Thank you for coming. So today, thank you for coming with this great weather, London weather. So today we have the opportunity and the pleasure of having very interesting presentations. So the reason why we're doing this event is our department and environmental design and engineering at UCL is celebrating 60 years. And the smart buildings and digital engineering is one of the research themes. So with the hope that we can get the discussion going around this topic and the opportunity of having certainly key people like Stephen and Phil here in London, it was a good opportunity to meet together and get the chance to talk about this topic. So we're going to be very quick. When I joined UCL 10 years ago with Ivan, there was a lot of understanding that digitalization is going to be quite important. And since then, we've had quite a lot of new developments. For example, this rise of AI is one of them. But really that focus around data and the opportunities that this might give to us is very important. And there's a lot of people, both from the Energy Institute, the Institute for Environmental Design and Engineering, and other places within this year that are working with data. And so what we thought is it would be a good and understanding what the value is. And SBB is one of these activities, and there is plenty within UCL and this year. So within that smart buildings and digital engineering theme, research theme, we have been developing quite a lot of activities, and here's kind of a high-level and broad research agenda. So we're looking to develop an understanding of how buildings are working, and more importantly, taking it from the perspective of the data that might be collected. So digitalization is a broad term, and there is a lot of opportunities there. And we need to understand how those buildings are working in isolation and embedded within a broader context. I think this is becoming quite important. So the methods that we're using is we design and develop models. These models can be physics-based models, or it can be data-driven models. We develop and deploy digital twins, and then we look at understanding how those models can help us explain the fundamental phenomena. We go almost to this side. It seems that this project, I'm going to highlight it on. And then, and how we can use that to optimize energy use. Our main goal is to create impact around different directions. And that impact can be generation of knowledge and knowledge sharing, which the discussion today about IEA annexes is very relevant, it's very important. We're looking at methods, tools, and new knowledge and how we can share this towards generating and accelerating the adoption of better operation and how we can understand our buildings, both in isolation, serving a purpose, which is serving occupants and users, and also the emerging reality of not being seen in isolation, but being part of a more wider and integrated system within the data. So in that perspective of doing impact, we have been undertaking a number of activities. And also there is a master's program which seeks to address skills gap, which is always relevant. And Valentina, who is leading the program, is going to talk about that very quickly.
Thank you. Hi, I'm Valentina Marincioni. Some of you know me. I'm the program lead for the Smart Buildings and Digital Engineering Masters. I think the main point of the Masters is that, well, UCL is a research-led institution. So all our research, then we aim to use our research to then have impact in the industry, in our case, for example. And as part of this, our Masters really takes a lot of the research that is done within the team and brings that within the wider industry. So that's our aim for the Masters, to really link with the current research, but also be relevant in the industry. So today is also a great opportunity to have some of our graduates and some of our students, because in 2 days there will be the graduation celebration. We are on our 7th year of the program running. And of course, the program has been evolving with research and with industry, with the help of the advisory board, industry advisory board as well. So it was a great opportunity to have this event and have some of our alumni. So you will hear about the work that one of our recent graduates have been doing, and also to showcase some of the research that our lecturers are doing. So it was great. Thanks, Dimitrios, for inviting also the MSc to be part of it. After this, we're going to have a social event to celebrate the graduates, which are graduating in a couple of days. So you're all welcome to join, and it's going to be joined with the day after the event.
So without a lot of delay, I think we have a very packed 2 hours of presentations and very interesting speakers. So in 2019, in the first floor, we had the last preparation meeting of Annex 81, then decided to call it data-driven smart buildings. And last week we had the new preparation meeting of Annex 96, which is that continuation on grid integrated control of buildings. And the main person that has been driving this and leading this, and you'll see that there has been quite a lot of consolidated learning and understanding, has been Dr. Stephen White, who's leading the energy team at CSIRO in Australia. And he has been doing a lot of great work around driving the annex and driving and great outcomes. And he's going to be talking about, now that the annex is coming to a close, what are the main findings. From UCL, Professor Paul Roosevelt, Dr. Virginia Gore, and myself have been involved. And so a little bit of that work has been our contribution, but I think it's all interesting.
All right, thanks very much, Dimitrios. It's brilliant to be here. And it's particularly, I guess, it's been a joy to work with Dimitrios and Paul and Virginia over the last 4 years now on this particular annex. So whilst I put my name down there and take credit for everything, really it's great giants of thought like Dimitrios and Paul and Virginia that have done a good chunk of the work. And it's just for me to sort of tie it up. Virginia, perfect timing. To replay the findings of what we've done. You know, this is 3.5 years work, so this is a whistle-stop tour. I'm sort of focusing, I guess, on it from a more of a philosophical perspective. What is the impact that this thing called digitalisation could have? What are the issues that we would face? And what can industry and government do about it? So the presentation is less about individual research as so much as what does the research actually mean? And particularly, what does it mean for industry and government? So data-driven smart buildings was the name we came up with. And, you know, our goal is to support adoption of software-based energy productivity solutions. That's a long word. It sort of encapsulates these sort of ideas of AI, artificial intelligence. And we kind of divided the task of this annex probably into 2 different components. One bit here is the data infrastructure piece. You can't really do data-driven smart buildings unless you collect data, surprisingly enough. So we have all the different data sources, we're housing that and structuring up the data so it's available. And then the second part of the story is, well, now that we've got the data, what useful things can we do with it? This is the International Energy Agency. So clearly, in terms of the energy productivity solutions that I put up there, they're all energy focused in this context. In terms of the structure of the annex, subtask A is focused on that data infrastructure. Subtask C captured the applications that in a general kind of a way. And subtask B, because we had so many people interested in model predictive control, we actually did a specific subtask on that. But as I say, it's not just energy that data-driven smart buildings would be useful for. This particular infographic here from a smart buildings online journal feed called Memory looked at different AI startups in the year 2021 and what they were actually focusing on. So this energy management and sustainability is this green blob here, 83 startups there, but you can see there's all these other different things as well. Security and access control, space, occupants, centric experience and stuff, predictive maintenance. So clearly, if you're a facilities manager, this is interesting stuff. So the infrastructure piece, we would like to think that the infrastructure piece from subtask A sort of caters for all of these things, and it's not just for energy, and ideas of value stacking so that you build the data platform once and are able to use it for lots of different things. The title for this slide is Scaling AI. So how would you go about scaling AI there? Well, or why would you... What is it that makes this a scalable thing? One part of it is the ability to use data-driven algorithms. These are relatively agnostic in that they see the data and they process the data and they give you results. And that means that you don't have to send in high-paid people to go in and interpret stuff. The algorithms process the data directly. And ideally, you may even get some additional value by identifying unexpected patterns using your data-driven algorithms. So it's the algorithms themselves, but it's also the data infrastructure piece. I guess if you look back historically at our non-residential buildings, ruggedized SCADA type building management systems and the like, and yet our mobile phones have obviously gone into consumer electronics and stuff and are managing data in streamlined, low-cost kinds of ways. So ultimately, it's that using IT infrastructure, borrowing that from our mobile phone kind of applications, and then processing data to extract value in a data-driven way. And ideally, for this to be scalable, is that it would somehow rather be self-service deployment. The analogy, or the grail, if you like, that we were shooting for in this particular annex is that just like on your mobile phone, you go to the app store, you download your app, it self-configures, and it just works. It's kind of the dream. I'm not saying we're there yet, but that's the dream. And broadly speaking, the buildings industry is behind on this kind of thing relative to our consumer electronics. So that's the general flavour of what we were doing. So let me now dive into some of the results from the different subtasks. As I said, subtask A was around data sharing and the data infrastructure that enables all of this. And I guess we somewhat assumed that the good things that are going to happen here are all going to become about because we have cloud-based data management. That is not a given. I think in Australia, if I kind of talk to my facilities managers, about half will say, well, of course we're going cloud-based, and the other half will say, not over my dead body will we go through a cloud-based management of our buildings. But the reasons why you might do it is remote access to services. You don't have to physically turn up at the building. You can just get on your PC or your mobile device. And then you can share that information around the various staff that need to have access to the results of the apps. And specifically facilities management, for example, truck rolls and stuff is all around getting information to people and making sure that we can do as much diagnosis before we hit the truck roll button. If we get to the cloud, we can also consolidate data with other third-party data sources like weather data, electricity, market data, and things like that. So we have a richer data set, more things that we can explore, possibly more insights that we can generate. And so the configuration, given that we are assuming cloud-based data management for Annex 81, is we have this sort of concept of the data layer. That would be instantiated on some sort of data platform. And this data layer is a kind of an abstracting arrangement that can hoover up the data from all the different sources, from IoT sensors, BMSs, third-party cloud sources with APIs and stuff, bring them into the data platform, put a security layer over them so that only the right people get to see the data, and also structure the data so that it's more usable. And so you can see standardized interfaces to actually extract this data is core, and then making the data available through permission controls into the various applications that we might want to deploy over the top. So I guess this data layer piece was a core part of what we were trying to do. Don't expect you to read this, but we did lots of industry surveys, voice of customer type work, and of all the things that we talked about when it came to all these different services that we were putting out there as things that you might want to do, data and data quality was kind of the core piece that sort of raised the temperature level for people. When you talk about analytics, it's all about data management, right? Data quality, data management. It's not a secret that in anything data-driven, 80% of the effort is in the data part, I guess. So, you can't underestimate, if you like, the importance of getting the infrastructure piece and the data management piece to make it happen. Probably this is my favorite here from a facilities manager. It's like going into a library and someone's got in there before you and messed it all up, and they've swapped all the books around, and you spend a day trying to find something which should be categorized properly. Sound familiar? Being in the world of buildings data, I'm sure you have. And then there's a bunch of solutions there that they provided that I'll talk about later. All right. And so if that data management piece, that data cataloging, that sort of analogy of like the library, then how do we make it available? Do we use the Dewey library system like that? And we agreed that the FAIR data principles was what we should aspire for in our buildings. That is, our data should be findable, accessible, interoperable, and reusable. And you go through all the various things that are required to achieve these FAIR data guiding principles, and a lot of them have got this word metadata attached to them. If you've got data coming out of your building, 4 to 28 milliamp signals, 0 to 10 volt signals, and what have you, really, what are they other than some sort of electrical thing? You're going to attach metadata to it to give you an understanding of what the data is and to give it structure to then make it findable and at an informational level, interoperable. So we had an entire activity relating to this idea of metadata and using metadata management to make data machine readable. That is, the machines can go in, they can query a database, they can find the time series data that they need because they can call the requests based on the metadata. So in a real building, a physical building, you've got a whole bunch of different pieces of equipment, if you like. They're all throwing data out there. And I think most people would say there's no shortage of this data, but it's this metadata model, which is the important piece that creates the contextualization. It says that this is a temperature sensor. This temperature sensor belongs to room something or other in wing something of a building. It's connected to this air handling unit. So you get this sort of hierarchy of information which allows you to query the database. So we did an entire report on reviewing the various metadata schemas. These are the standard ways of representing that metadata. And we looked at the idea of the metadata model. That's where you use the schema and you model your specific building to represent that what all these various data points actually mean. And I guess the way there is ongoing standards work, I guess, to improve these metadata schemas. But one of the things, I guess, that's lacking at this point in time is this ability to work out how much of this modeling, semantic modeling of a building you would actually need. If you've got thousands and thousands of data points, do you need to know all the metadata about every data point? Or is there some sufficient level of modeling that gets you, 80% of the things that you need to do? And in an idealized world, not saying that this is today's world there, when you have a software application, it would say that what it needs, and you would match it up with the model of your building, and then there would be an assessment of have you got all the data you need, and outcomes are true, false, goes back to the people modeling the building and says, you need to find this extra stuff. If you could have that up front, you would save a whole lot of pain and heartache buying a product only to realize that your particular building doesn't have the data available to actually do it. So this idea of sufficiency is something that will need to grow. I like to think of it back in the day, to show my age, where you go out and you buy a piece of software. This is on a floppy disk or something like that, and it would give you the requirements for running that program. It might be 24K of RAM and 600 kilobytes of hard disk space or something like that. It's explaining what you need so you can match it with your model. Lots of work to do on that. Other part of the fair data principles, reusable will obviously go down to ideas of data governance. We like to think in commercial buildings that most of the data is not private or personal data, but there may be personal data involved. You need to know your 6 bases for sharing data, and you need to get very familiar with the different sorts of controls that you can use to be able to get permission through ethics to be able to use that data. And the data sharing controls are in the sort of 5 safes data principles. And the more personal the data, the more stringent the controls you have to apply. We did a bunch of case studies of data sharing, and to be honest, you guys in research land, you're pretty darn poor at this. It would be my thing. Yes, you've got your ethics committees, but just because you're doing public good research doesn't mean that you satisfy the public interest criteria for handling of data. So a lot of toing and froing, sort of trying to pitch research as suitably controlled and good for sharing. We assessed data platforms. We had 11 criterias there of what a good data platform would be to instantiate this. And to be honest, there's lots of good platforms out there. The things that we found were most likely to be differentiations between different platforms was around how good the metadata management was. Often these platforms have grown up in a fairly higgledy-piggledy kind of a way that's led to proprietary metadata schemas and things like that. So, going for an open schema like Brick or whatever is what we would recommend. The permissioning system, that means that you're in control, you've got sovereignty over your data is a core one, and that then links into, if you've got sovereignty over your data, then you want to go out looking for third-party apps that will give you value rather than being locked up in just a single provider's system. Subtask fee on model predictive control. So we went out and and this was kind of pretty much the same sort of process for each of the software applications. So we're now on the software application side. We reviewed the various sources of data and some of the exemplar installations, and then created data places where you can go to get good data for doing your research. So I think we got in from over 20 buildings. We narrowed that down to what we thought were perhaps the 6 best high quality data sets. And there on Mendeley, you can go and you can publicly available data, and you can start doing your own model predictive control research using that data. So model predictive control. You have your HVAC system, it's controlling the HVAC and into the occupied space, and you discover how well that's doing. That's all happening in your normal building. And then model predictive control has got, in addition to the physical system, it's got a model of a virtual model of what's going on. So this is what we call the control-oriented model. And that can be queried by the MPC controller or optimizer according to whatever your reward system is. So what we did there, in addition to getting data sets, what we did is we used the bot test framework where we took out the real building and we put in the building emulator, because to be honest, you can't really be, from a research perspective, be playing around with people's buildings. And that way we were able to benchmark, if you like, or compare all the different control-oriented models, grey box, white box, black box, etc., on a common basis, and using common reward functions in terms of Kelvin hours of thermal discomfort, cost, and emissions. So here's just a sample of some of those comparisons. This one is using the best test heat pump hydronic test case in the bot test. And we've got thermal discomfort on the y-axis. We've got the actual cost in energy cost of operating the building on the x-axis. X there is your traditional baseline control system, which is built into the emulator. And here's all the different test new optimization results there. Interestingly, 3 of those are model predictive control and 2 are using reinforcement learning for doing the optimization with knowledge or foresight of what's going on. You can see about a 20% reduction in energy consumption, and the model predictive control did a little bit better than reinforcement learning. Subtask C, we looked at KPIs for benchmarking. We looked at fault detection and diagnosis, and also building to grid. Just touched on building to grid, now we're expanding on that in Annex 96 in depth. So big review, classic sort of thing, big review. What are all the KPIs out there in the industry? We broke them down by occupant-centric aspects, use of smart technology, building energy and maintenance, and building to grid integration. And that broadly reflects the SRI, Sustainable Readiness Index, which is part of one of the EU directives there. So something like 450 different KPIs were identified. We then went into 5 case study buildings, and these were relatively well instrumented buildings. And we worked out, could you actually calculate the KPI or couldn't you? And the answer is only about 25%, a quarter of the buildings. You could actually even think about calculating those metrics. So a lot of stuff proposed, not a lot that's actually practically usable is the answer. And just drilling into the building to grid example there, again, we went out, we reviewed where are all these data sets. We got some from our own Annex 81, we got some from Annex 82, we got some from open data repositories, and we went there and tried to find out, well, okay, what can I provide everyone in terms of high quality data? Most of them out of scope. Contacting them to get more details, no reply. And actually what came out the other end of the sausage factory there was about 16 data sets, which we could use in some form or other. So again, I think it's on GitHub that we've got the data sets that come out of that are usable. And then when you drill into the data and you look at what data was needed by the KPIs for flexibility, and you looked at whether the data set actually had that data, what you see is that we had lots of data around indoor temperatures, but to be honest, not many of the KPIs required it. So there was this mismatch between what KPIs were required and what KPI data was actually available. So a lot of work around what is the right data for collecting and how do we get it. Fault detection and diagnosis. I would say that rule-based fault detection and diagnosis is relatively common, but data-driven fault detection and diagnosis much less common. Again, 7 data sets, particularly from Lawrence Berkeley National Labs. They're high-quality data sets that are available for people to use if that's your research interest. And then a survey of industry as to what their needs were. And what you can see is a lot of the things that are required are around the implementation side of the thing, rather than specifically around scientific new algorithms. Last subtask D, case studies and other cross-cutting. This was a fantastic work that UCL did. Created a web portal that you can go in. There's around about 20 case studies of different uses there. Virginia, if you want more information on these case studies, she's the person to look at there. And these are kind of the story of implementing data-driven smart buildings as much as anything else. And the stories around data quality and management, starting to sound like a broken record here, I know. Technology specification and implementation, stakeholder engagement, getting the right people at the right time and managing your occupants and things, and those governance issues. The things that started to come out were strong factors. And we ran a bunch of AI competitions. We did a load disaggregation. That's taking site metadata and breaking it down into its constituent components. So we gave ground truth data to contestants and then took away the ground truth and said, can you predict for these these new unseen buildings? BOP test was a control challenge. And so we ended up with good participation in each of those, and there were cash prizes. Most recently, we've just run a competition brick by brick, which was actually taking time series data from sensors and using the brick metadata schema, trying to match that the brick schema classes to the actual sensors themselves. We ran that on AI Crowd, got 399 participants, 31 teams, and significant prizes for that. And in some cases, the beauty of AI, or where AI may well have the most benefit, is actually in the infrastructure creation part, not just in the actual useful applications. And then we looked at, we interviewed industry across 3 continents, talking to industry leaders about what they thought would be needed to actually grow this industry even more than it is at the moment. Theme, and I've got 8 themes here. Theme 1 is around provide information. On the whole, AI and data management was seen as, industry sees that as relatively complex technology, and a desire for more information in terms of guides and standards. There was a desire for more and more case studies and to build up the website that UCL has created there. And one way that was thought of doing that was by actually getting government to put its money where its mouth is, so to speak, and use its own cohort of buildings to drive the market. And for government then to use researchers and innovators to independently evaluate and create the information that feeds back up there into theme 1. Workforce skills and capacity. There was a strong desire there. A lot of industry people saying getting people who understand both SCADA and IT was a serious challenge for them in buildings. And then around incentives, interestingly, theme 5, that is give me the money, Didn't come up so, in the prioritization was probably the least prioritized there, but definitely can we please play on a level playing field with energy management in our buildings there. So can we get fair reward for any flexibility or demand response that we can extract out of our buildings? Because the general vibe was that this stuff pays for itself if done properly. And then here's the last ones, theme 2 and theme 6, both around that data stuff. So I showed you the sort of speech bubble there with all the sort of comments. Well, this then distilled down into, can we actually have some sort of concept of digital ready certification? So, in the sticks, carrots, tambourines kind of policy framework there, can we create a tambourine that is a celebration for getting your digital readiness of your building? And from a risk management perspective, if government was to say, you need to collect certain data, then that would, because there was that regulatory requirement around what specific data needed to be collected, that would manage risk as well. And so this is where we're at in the current industry. Every one of those sort of software applications, I talked about it before. Typically, you go out and you buy the software application, and what you're also doing is you're buying a whole bunch of IT infrastructure to enable that all at the same time. It makes it a complicated purchase and relatively expensive. So what we kind of were pitching was that somewhere we break it into a two-step story. One is establishing that data layer. You remember I mentioned data layer as being kind of the core. You establish your data layer, you get your certificate that you're digitally ready, and then the world's your oyster. You can start picking off all the different applications that I showed in that sort of memory infographic at the beginning. And that would be a cost-effective and staged process for deploying digitalisation in buildings. In Australia, I've used the research that's been done here, and we've created some specifications around this digital ready, and we've got it now in the draft 2024 National Construction Code as a set of criteria that you could deploy to get through code. And also deployed it for what's called a foundational energy management information system. This is the basis you achieve these things, tick, 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 and you get some certificates which are a tradable commodity in Australia. So you can make money out of that. And that's all being pasted together into the format for the International Energy Agency as a policy recommendation. You can see the targets. Right now, you should be doing this anyway, because it should be cost effective. But in the IEA net zero by 2050, there's some targets at 2030 and 2050 there around new buildings becoming digital ready and then existing buildings. And here's all our recommendations. You can see the themes that I mentioned, but then there's kind of definable actions as well. Broadly around your sticks, your tambourines and your carrots there. That is regulation, information and incentives. So that's, if you like, our pitch, particularly to government, on how they can actually drive this industry. So last serious slide here, an absolute cornucopia of deliverables and things that you can use. There's a bunch of informatory reports, one for each of the three subtasks there. Then there's a series of more detailed reports, a data-driven smart building state-of-the-art, survey of metadata schemas, etc. Here's our report, opportunities for government leadership, if that's not an oxymoron. And then here's our bunch of data repositories and stuff to get you started on your data-driven research. And then there's a bunch of tools. We've built ourselves a flexibility calculator tool. And last, doesn't come out color-wise, it was meant to be a different color, but can't thank the guys enough for the case study repository, which is a fabulous resource. I don't know, have I taken up too much time? There's your URL to actually find all those resources.
So thank you very much, Stephen. So let's read quickly to Professor Paul Roosevelt, who's from the UCL Institute, and he has had quite a lot of experience in working and handling huge data sets. So I think one of the work that he has been doing quite recently is this national UK National Census database, and Paul will be talking about that and how that can be used for its buildings.
Thank you very much, Demetrius. I don't have a world of experience in dealing with large data sets, but I'm very fortunate to have a team of people who are, and some of them are in the audience today. So thank you very much to members of the team here. What I have is an overview of the systems and so forth that we're building, and I hope to impart some of that to you today. So coming out from Stephen's focus on individual buildings and imagining a world where across many buildings, perhaps a whole building stock, we can begin to harvest, store, interrogate data from every building on things like what's happening inside them, how much floor space there is, what type of construction materials are used, how much energy do they use, of course, their age, value, and much more. So what we might regard this as is a national digital twin for the building stock. Now, I know I'm running fast and loose with the word digital twin here, but I have seen it used in this context before, but I respect the fact that it's more traditionally a twin which is interactive with the physical asset. But why would we need such a thing? Well, certainly in the UK, I think it's important to start to look at the building stock in context. And we've got some emission clouds here, and I won't get you to guess which emission clouds are associated with which particular bits of UK infrastructure. But if we take UK railways, infrastructure value of £332 billion, emissions 2.3 million tonnes, owned by 28 companies, so relatively easy to deal with. And they have their own digital systems which are being used in this area. UK water industry, £90 billion, 11 companies, 2.5 million tonnes of carbon dioxide. So significant, but perhaps not the most. Electricity industry, difficult one to call, because if we deal with everything in terms of the scopes, then scope 2 emissions are largely associated with the electricity industry, but in fact, of course, those emissions really arise in the buildings and other facilities that use them. So the parasitic loads in power stations up and down the country probably don't amount to very much CO2 in the context of the bigger picture, but it's £196 billion. It's for 37 companies, and they are actively building a national digital twin on top of the existing digital systems that they have for the national grid and so forth. So the one at the bottom, you probably guessed already. First of all is UK non-domestic buildings, which is around about £1 trillion worth of assets across 2 million premises, probably of the order of 1 million owners, some of them landlords, some of them individual owner occupiers and so forth. And then the domestic sector, probably some about 30 million homes, 8.7 trillion pounds, and around about 23 million owners. So somewhat more difficult to deal with in terms of the ownership. So if we think about 32 million units, value 10 trillion pounds, 24 million owners, more diverse, more valuable, more owners than any other infrastructure asset in the country, then probably more in need of a digital twin than any of the others. So what I want to talk to you now is building this digital twin and how we have developed it and what it is composed on. So first, a little bit of history. At UCL here, the Building Stock Lab has been developing these digital representations of building stock for the last 10 years or so. And we have this model called 3D stock, which I'll say a little bit more about in terms of the content of it in a moment. But that's been used in recent past to build a digital representation of all of London's building stock, the London building stock model for the Met of London. And using that, we built the solar opportunity map, which maps all of the surfaces in London on roofs and the surrounding areas, understands the exact amount of solar radiation arriving on the surfaces, and allows you to pick any building and understand what the solar potential will be. And a shout out to Ivan over there who developed the original model for that. And we've gone on to use this model to help local authorities begin to plan scenarios for decarbonising their housing stock and other buildings. So going back to the National Building Database itself, the purpose as set by the government department, the Department of Energy Security and Net Zero, that has commissioned it, is to create a record of every building in Great Britain, England, Wales and Scotland. Unfortunately, we had to leave out Northern Ireland. The data systems used in Northern Ireland are slightly different to the ones that we use in England, Wales, and different again to the ones we use in Scotland. And having added Scotland to our previous model of England and Wales, we felt it was a bit too far to go to bring in a fourth country. It would have added to the workload and complexity. But we've subsequently looked at the situation with Northern Ireland. We think that it can be added to the database at some point in the future without too much difficulty. We're characterizing key features of construction geometry, the categorization of buildings, primarily in terms of their activities and uses. We want to particularly examine the validity of the energy performance data that we hold at a national level, which is typically the energy performance certificates or the display energy certificates, to see how well they actually represent the stock. And I'll come on to in a moment how we do that. And as part of the process, we've developed a method so that the Department of Energy can simply update this model in the future as new versions of the data sets become available. I won't say press of a button because it's quite a bit more complicated than that, but we have prepared a detailed set of instructions for them, shall I say. So one of the, and I'll say more about the atlas later, so I'll skip those, come back to those. So the activity classes that we're focusing on are primarily non-domestic, and you can see them all listed here. So these building types we will develop in a lot of detail within the database, but we're also covering domestic buildings, and we'll do so with a slightly lighter touch. What that means is that we won't have all of the rich data set that comes with the non-domestic data. But importantly, we will look at domestic in detail where it's combined with non-domestic. So where we have mixed use buildings with, say, for instance, retail on the ground floor, offices on the first floor, and then residential or domestic for the next 2 or 3 floors above that, we will represent that whole building in detail. Within each of these activity classes, as we call them, there are a series of what we call activity groupings or subdivisions, if you like. So for instance, in hospitality, we have hotels, we have pubs, we have cafes, and so forth. And you can imagine the way that some of these other categories, classes of buildings split down, and we have some 38 subcategories altogether. So how are we building this database? Well, first of all, we're assembling a whole series of national data sets, some of which exist in the public domain, and some of which are only available through government because the data is confidential. So it includes things like the Ordnance Survey address-based system, which is the, if you like, the spine of the whole thing. And it uses a mechanism called unique property reference numbers, and they are the basis on which we connect a lot of the information in the data set. But we're also bringing in data from Ordnance Survey polygons, so that's the footprints of the building, land registry, which tells us about the boundaries around sites, we use LiDAR data from the Environment Agency, and we convert the point cloud from the LiDAR data into three-dimensional representations of the buildings, which are then superimposed on the Ordnance Survey polygons to give you a full three-dimensional representation of all buildings. We associate the EPCs and DECs, display energy certificates, energy performance certificates, on a premises by premises basis. So for instance, if a building has a number of occupants and each occupant has an EPC, then we associate all of those EPCs with that building. We use the Valuation Office Agency data. So the Valuation Office Agency is an organization that helps set the property rates, both commercial and domestic, and it has measured floor area data for all, well, not all, for most non-domestic building types. And although it's publicly available, it has a very specific license associated with it, so it can only be used in the public domain for rateable value purposes, i.e. to do with the property taxation system. But working for government, we're able to use that data in other ways, and therefore we can use the floor space data, which is floor by floor in every single building that they rate, with each of the activity types. So for instance, offices, circulation space, or other types of ancillary space, broken down into individual floor areas by floor. We most importantly are able to bring in the actual energy data. So the government has access to annualized meter data for every meter in the country. The challenge is matching that meter data to the properties. In the past, when the government has attempted this through things like non-domestic need, which is an annually published version of the non-domestic stock, they achieve match rates of the order of 50 to 60%. Because we use a three-dimensional model and we understand the relationships between premises and buildings, our match rates are in the high 90%, so 97, 98% typically. That means we can give a very good understanding of energy use, not just at the premises level, but at the whole building level. So I think I've covered a number of the databases there. There are some other databases that we use, which I won't go into because some of them are kind of sector specific. They're related to hospitality or some other sector. But we want to also ensure that this database is reasonably representative, and we also want to try and understand what it means. And in order to do that, we conduct a number of, first of all, telephone interviews with a large number of respondents from each of the different activity classes, in which we, first of all, ask them, we think you're a shop. Are you a shop? And they come back and say, tell us, no, we're a cafe. So we have some understanding of the extent to which the Valuation Office Agency data is really representative of what's out there in the stock. And the second round of telephone interviews that we have conducted, which we call insight surveys, have asked organizations about things like how they operate their buildings, what patterns of use they have, when they switch their heating systems on and off, and so forth. So we have a reasonably good understanding across a sample of the data. It's not a massive sample, I have to be honest with you, but it gives us some feel to what the data actually means in the context of how organizations operate in buildings. And then for an even smaller sample of buildings, just 72 buildings, we actually went in and measured everything, and from those measurements produced an IES model of which is equivalent to what you would do for an EPC, and we then copied that model into a different modeling platform, Energy Plus, which we commonly use for dynamic simulation, and in comparing. And then we calibrated the Energy Plus model using actual half-hourly meter data from these 72 sites. That then allowed us to look at the energy use breakdown into its individual end uses, things like lighting, heating and ventilating, and so forth, and compare what our model says to the EPC model. And that is intended to give us some confidence in the wider data that we have across the nation for that breakdown between individual end uses. And that all comes together and we produce this national buildings database. So, piece of work we're working on now is phase two. We published a report in February 24, I think it was, yeah, on phase one. This was kind of a pilot or proof of concept project where we produced a light version of the stock model for the whole of England and Wales, and we did a deep dive into hospitality. So just some headline figures of the sorts of insights that you can get out of a model like this. And in offices, shops, hospitality, activity classes, some 50% of premises have a heritage status of some form. So that includes conservation areas and various levels of listed buildings. That's something that's obviously going to impact on the extent to which you can retrofit some of those properties. The scale of properties is quite interesting. I mean, some 94% of premises across the non-domestic stock are less than 1,000 square meters, but 10% of premises contain over 60% of the area. So, you know, we have a very long tail, very small group of large occupiers, a very long tail of small ones. Before we did this piece of work, the government had to rely on the Valuation Office Agency data on its own. And it doesn't actually record floor space data for things like hospitality. It rates them based on bed occupancy, bed spaces, basically. So their estimates of floor space in hospitality were something like 14.9 million square meters. And there are various other attempts in the past to try and get this. The BEES project, which is in some sense the predecessor of the National Building Database, which was started in 2016. They estimated 49.4 million square meters. With the methods that we've used, we feel that we've got a much more accurate figure for the total, and it's close to 60 million square meters of the floor space. So we've been able to improve on some of the uncertainties in the data from the past. And I referred before to this issue of mixing of building types, and we were very surprised to see that 48% of non-domestic premises share a building with another non-domestic premises. So, you know, offices as such do exist, but they quite often are mixed with retail and other sorts. I guess we know that from the high street. But a further 23% of those share premises with a domestic premises. So this level of mixing is quite important when it comes to understanding things like retrofit, things like the strategy for district heating and so forth. So just to finish off, where are we now? Well, we're quite close to the end, thank God. We should be submitting our final report to the department next month, and wrapping the project up at the end of July. I don't imagine anything will be published for 5 to 6 months after that, because that's the time that it usually takes to get through the system. What we'll be producing, so the whole database goes to the Department of Energy Security and Net Zero. It will potentially be available to other government departments. Ministry of Housing have expressed interest for fairly obvious reasons. We'll be publishing a final report, which will be publicly available. We'll be publishing national and regional aggregated data on each of the activity classes. And finally, we'll be producing a synthetic population. And the synthetic population will represent each of these different activity classes, and in many cases, the subgroups, the activity groupings at the middle super output level, which is fairly small areas. And we will provide data on the list of things that I presented there, and probably a few more. So this will allow researchers and others to conduct studies based on quite a fine area, quite a high resolution, much higher resolution than has been possible in the past. Thank you very much.
So the next presentation We started from Australia, we moved to the UK, and now we're moving to the US. And who better than a British person to give perspective about controls design. So Dr. Davis, he used to be working until a few years back at Lawrence Berkeley National Labs in the US. And he has worked on many things. He's fellow professor. He led the buildings group, building simulation group there, and organized the building simulation conference, president tributes USA in the past. So lots of experience, and he will be talking about some of that experience that has been consolidated in how we do integration and operation of controls.
All right, thank you, Dimitri. My presentation describes the Open Buildings Control Project, whose goal is to define a new controls process to integrate building design and operation. So clearly this is going to, initially that's going to apply mainly to non-domestic buildings. In principle, it could apply to all buildings. Project is led by the Lawrence Berkeley National Lab, often referred to as LBL, and is funded by the US Department of Energy and the state of California. It's a very different political environments within the US at the moment. You don't say more. This project, the Open Building Control Project, involves a number of industry firms, which I'll list at the end of the presentation. The project started in 2015. I retired from the lab in 2019. So this presentation largely focuses on the foundations of the project. So I'll present the current status at the end of the talk. Well, I don't have to tell this group that the disconnects between control system design and implementation play a substantial role in the performance gap. Problems include a lack of design tools which can be used by the mechanical designer to generate and test control strategies. Further problem is the lack of tools which can be used to generate and test sequences of operation before the control supplier is selected, and hence before the corresponding hardware is known. A major problem, arguably the major problem, is the lack of tools to ensure that the sequences of operation as designed get implemented correctly, which goes back to the performance gap. Other industries, including automotive and aeronautical, do have such tools and depend on them to produce robust control through automatic implementation of validated sequences of operation. So I suppose maybe I'd really like to check here, but how many people are familiar with the term sequence of operations? Okay, a minority. Okay, a sequence of operations is basically the programming that goes into a building control system. So the goal of the Open Building Control Project is to develop a controls process that is robust and works from a business perspective, guided by an industry advisory board consisting largely of controls practitioners. And whereas that's being performed in the US, this work is, a lot of this work is quite generic. And of course, ASHRAE claims to be an international organization. Enough said on that. And so the main aim of the project is to develop a set of software tools to support this process. The first step has been to develop a set of tools for designers to create and verify control strategies in software. Our tools are designed to export sequences of operation to the actual control suppliers who can then use that information to bid for the controls, hardware, and installation in a construction project, and tools to do to compare as designed and as installed sequences are under development. So slowly, I have to say, at the moment, post-COVID, and then with political changes, one thing and another, Oh, I'm sorry, yes. It's not a but, it's not smart enough to, thank you, appreciate that. All right, I haven't done this for a long time. As you might guess. Let's see, okay, all right, I can try this. So open building control is based on a language developed in the project. This language is called Controlled Description Language, or CDL. And CDL is used to express, manipulate, and transmit building control sequences between the different players involved in the process of design and installation and operation. CDL includes a graphical editor and a library of elementary control functions. And this library must be supported by controls companies for them to use open building control. And I'll come back to the state of that sort of commercial adoption at the end of the talk. Just read this very quickly. A few words on this particular slide, but illustrating the block diagram nature of the language, and also emphasizing the fact that it should be broadly adopted. It has to be non-proprietary, open source, and not manufacturer specific. So manufacturers have to adapt themselves to use this standard model, a standard way of representing control strategies. And so just a few development challenges that we ran into, we identified in this project. First of all, support for larger buildings. Managing the complexity and computational burden of simulating hundreds or even thousands of control loops is obviously substantial. This, we're not talking about hourly simulations, so much shorter timescales. Another problem or challenge is that many building projects have no energy model by the start of what I think is called here developed design. Is that equivalent to the detailed design, DDs, and it's that point at which you are ready to design the control strategies and turn them into sequences. So given that most building projects don't have those models, ties back to what Paul was talking about, we'll use prototype building models. So these are sort of generic models that are configurable in terms of climate, use patterns, basic geometry, and system types. The language used to express the control sequences must be generic, as I mentioned a moment ago, but must easily map to proprietary control products. Otherwise, it's going to be too difficult for manufacturers, controls manufacturers to use this approach. And so to guide us in that, we have an industry advisory group, as I mentioned, and we are in fact working closely with ASHRAE. Well, another reality check. How many people know what ASHRAE is? Okay, just checking. All right. Further question then, how many of people are familiar with ASHRAE's guideline 36? Okay, so about half. Well, so for the benefit of the other half of the audience, this ASHRAE guideline relates to high performance sequences of operations for HVAC systems. So it's basically a library of control sequences that are believed to be, and in a lot of cases tested to be, high performance in the sense that they will produce better energy performance and better comfort and low wear and tear and all the other good things that a good control strategy should achieve. And so what we have at the top of the slide here is the workflow for the that we've designed for the Open Building Control project. And so the first stage, first step is for the designer to select a sequence of operations, either from this ASHRAE guideline 36 that I mentioned and we'll return to, or from a company's proprietary library. I guess anybody here from a large engineering consultancy that has its own library of sequences. Well, that's good. And the third possibility, of course, is for on a particular project for a sequence to be created from scratch by the designer. In each case, the sequence is then in a standard open format. The sequence is configured for the project and then coupled to a model of the envelope and the HVAC system. So that's we're now into the second part of that big block there. So that point, this combination of the building model, building an HVAC system model, and the tentative control sequence can be then simulated to test that it meets the actual performance requirements for the building, for the project. Moving on, once the control system is installed, a tested sequence is uploaded into the controls hardware for functional testing. So functional testing is sort of an aspect of commissioning. It's where you actually, where the rubber meets the road in terms of does this thing actually work as intended. Control suppliers, I mentioned this a moment ago, this difficulty that control suppliers have to each have their own proprietary language. I mean, it is proprietary in the sense that it's specific to each company. They have their own way of doing things, and so one of the things that we've focused on in this project is to produce controls that will help them essentially adapt their products to read this controls sequences in this standard format. And if that doesn't happen, then this is dead in the water, but there are some encouraging signs there. So the goal is to support bidding, so in particular bidding for control system hardware and the selection of a controls contractor, leading to automatic implementation and automated functional testing. So a short case study. This is the first case study that we produce. If you have if you're a quick writer, or if this is going to be made available to people afterwards, I recommend the reports that are linked with the URLs on the screen there. There's not for the faint-hearted. There's more information there than you would dive into just out of idle curiosity. But if you're really interested in pursuing this stuff, then that report is a very good place to start. And so this case study involves taking a control sequence from this ASHRAE guideline 36 that I mentioned, and first of all, casting it into this neutral format, executable language, this so-called CDL, or control subscription language. And so you're going from natural language. So the ASHRAE guideline is written in regular text, you know. This actuator will do such and such when response to whatever, and that has to be turned into essentially executable code, which is what the control hardware needs in order to do its job. And so that's what happens. That's illustrated. Don't try and read the details here too much. Just to say that the this particular case study involved secondary HVAC systems, in this case, multi-zone VAV, together with an air handling unit. So that's where a lot of the work in building a control system and control sequences of operations for a commercial building. That's where a lot of that grunt work, if you like, goes on, because if you have multiple air handlers and many zones in the building, you really want to automate this process as much as you can. And so this next slide gives a flavor of that. On the top right, this is you see a representation of part of that sequence, and try and read it, but you can see that it consists of a number of different blocks, each of which does a particular function, a particular simple function, like it adds, or it does proportional control, or selects between different inputs, and then those are assembled together into what is in effect a control program for the building. And so for this this case study first, we picked not a whole multi-story building, but one floor of a multi-zone building. And so the core zone and the 4 perimeter zones. And this is a common way, common strategy in building prototype building models for this kind of study. And so you may or may not have seen these in the context of hourly energy models for research purposes. This is a whole different level of detail, in particular, modeling of the full airflow network. It models the pressure drops and the flows and the actuation in all the ductwork and all the pipe work of the HVAC system. And it also takes account of the effect of wind pressure driven infiltration on the airflow in the building. So this interaction between the inside and the outside, because the control system has to be able to deal with that. Your simulation model for analysis purpose just sort of probably just neglects the effect of the wind, for example. But if you're going to exercise a control system and make sure that it's robust, then you've got to model all these kind of effects. And you're also going to be modeling the control actions explicitly, which means you're using time steps that can be as short as a second. And then you want to get a picture of how this will perform over a whole year. So you don't do 365 days, you do typically 3 days a month, which are sort of statistically expected to be typical of each month. And if you make those approximations, which seem to be pretty good, you've got a high-end PC, it'll take about 100 minutes to run that compressed weather here. And so I think that suggests that this is actually technically feasible. That and of course, as computers get even more powerful, cliche, then it'll run faster, and you'll be able to do more kind of more testing and such, and play with different design alternatives. Okay, and so the results from this case study was, first of all, it was a it's a comparison between standard conventional control sequences that are used in office buildings and comparing that with the supposedly more efficient sequences in the ASHRAE guideline 36 library, and see that there's significant savings in energy use. And so the main thing about that is not to say necessarily just that, it's not just to say that the ASHRAE guideline sequences are better, but it's to show that these tools can be used to compare different control strategies, different control sequences. Moving on from that, I'm going to skip over that. Okay, so if we're interested in deployment, which I think some people are in this room, this slide summarizes how the different players in the design team or the design and delivery team can benefit from this control subscription language and this open building control sequence. So the mechanical designer can customize and evaluate control strategies and sequences, and then include them in a bid package. I mentioned that before. And then the beauty of this is that because that sequence is part of the bid package, it's not just pages and pages of text, which is how things are done now, but it's machine readable. And so with the appropriate tools, the control system, the contractor can run that sequence through and see how map it onto, for instance, the hardware that they would use in the building, which will differ in detail from supplier to supplier, so they can figure out how the building control system could be designed with their products, and therefore produce a bid and then see if they are successful at getting the project. And then the commissioning agent can do the necessary functional testing once the control sequence is installed, to make sure that it actually does what it's supposed to do. All of this is, I think, quite a radical departure, a major benefit over the way things are done at the moment. So this is, in effect, my last slide. Not quite my last slide, but, and so this just summarizes what's going on at ASHRAE. So first of all, this controlled subscription language that I've been talking about is has a standards committee all to itself. And that committee is essentially codifying that language, and then it's been through, I think, one public review. It's ready for a second public review, and the prediction is that by the end of this year, this will be published. And the significance of that is that controls manufacturers will be able to say, right, this is the ASHRAE approved version of this control description language. It's not some draft or that could change under our feet. And so that's the point at which they have to make the decision to adopt this or not. Informal contacts have indicated that at least some of the controls vendors are very interested in doing this, because potentially, if this all works, it reduces their costs. And so they can underbid companies that don't use this, and the owner benefits, and in fact the controls contractor will benefit as well. So it's a win-win. Just get this thing, yeah. And so guideline 36 I mentioned, that was first published in 2018 and is being continuously enhanced as we go along. maybe Dimitri or Stephen can say something about standard 223, the semantic data model for analytics and automation applications. And I'm not going to say anything about that, partly for some out of time and partly because I don't understand it. So just the acknowledgements. I mentioned the funders, so we have to mention funders. And then the other organizations here listed in alphabetical order. So of particular significance to our being at the top of the list there. It's just alphabetical. These are all the companies that participated in the evolution of this project. With that, I just like to thank you and thank you.
So now I have the pleasure of inviting James Franklin, who is one of the MSc SBD alumni. So just give a brief introduction to James. He's also been outside the UK. You've been in Australia.
That's right. Yes.
Yeah. So he started as in the IT industry and then moved to the construction industry 10, 12 years ago, or a bit more.
Oh, wasn't it?
So
17 years ago.
17 years ago. So, and I met James because as head of BIM at Kier, I think that was your role at the time, he decided to also join the masters and enroll as a part-time student. So being head of BIM and working and studying, I guess it's been a busy period, but very successful. He's just finished the He's graduating this year, so well done. And also, you're now head of, you're a digital twin project director.
That's it, yeah,
at Kier.
yeah.
So it's great to see the breadth of our students, the fact that we have such experienced students mixed with much more junior and early career. So I see some of the alumni here, so it's great to see what James has been doing in the field.
Thank you. Thanks, everyone. I'm not going to read out that title. That's jumped up by one of our marketeers, but basically I'm going to be talking to you about how we're applying digital twins with the Ministry of Justice in the UK. Valentina has already done a great job of introducing me, but yeah, I work for Key Construction, one of the UK's top contractors. Obviously recently finished the Masters. Key learnings are that all the students are brighter than me, and I'm really old as well. So that's my key learnings, but no, I'm very grateful for the opportunity to learn under Valentina and Demetrius, and of course Ivan as well. So yeah, it's been really inspiring and a great foundation for some of the work that I'm going to talk to you about today. So yeah, you guys are a learned audience, but you know, I do have to explain this on many different levels, and there's digital twins, you know, many different descriptions out there. And we're talking about an operational digital twin. So we're moving outside of the world of design build, we're moving into operations, and we've basically got the physical building, we've got a digital representation of that building, and then we're ingesting data from the physical world via the building management system, via IoT and various other systems, applying data science, and then offering back better outcomes with the principal use case around energy efficiency, but we're touching on other things as well. So for the Ministry of Justice, why would they create a digital twin? Well, they've got a vast estate. I think they've got the second largest estate in UK government, high energy bills, aspirations to drive towards net zero, and lots of documentation telling them that they need to digitise their estate, make use of digital twin technologies. So, you know, everything's there to drive the case for them. We want to tackle the performance gap. I'm not going to explain this to you because it was explained to me by people in this room, but you know, obviously performance gap is there. We've got bigger drift as we go further through the life cycle. We can tackle that performance gap continuously via data and technology. A digital twin offers us a great framework in which to make that happen. So for our Pathfinder project, Pathfinder was HMP5 wells. That's a project we handed over in 2021. It had modern methods of construction and digital built in from day one. And as well as that project being a fantastic success, it was handed over on time and to budget, which is really rare for major projects. We also digitally handed over that project as well. And to help us do that, we employed a system during the construction period called Glider, and that helped us validate all that information from the supply chain. So all of the O&Ms, all of the as-built models, all of the asset data known as COBE. It's a huge data model, and we've just done a similar prison, and I haven't got the stats around this one to hand, but I know that in our asset register, we've got 30 million data points. And that data has all got to be validated. So we can't do that by observing it anymore. We need to use computers to do that. So Glider was a platform that enabled us to do that. And at the same time, in effect, it created an asset information model with all that data interconnected as well. Our contractual deliverable was to basically flatten that information and stick it onto a legacy system for the client called Viewpoint, which we did. But I was keen that we looked to see how we could leverage this information model in Glider into operations. And at the same time, our building technologies experts are saying to the Ministry of Justice, look, we've got an intelligent building here. There's lots of endpoints in the building management system that aren't necessarily being used. And in our aftercare period, we were harvesting data from the BMS, and we could see that there was different temperatures on different wings, on different floors. And we need to understand why is that the case, and also actually leverage that data and make it work for us. So we took those two principles together. We've got this information model, we've got building intelligence. Can we run a digital twin pathfinder? And that's what we've done. And this is quite interesting because this is the building, this is the house block design. That's a standardized design. It's getting repeated up and down the country by various contractors on various different sites. And we can have this feedback loop from, you know, not only from design, but through the data that we're collecting, analysing, and we can feed back into that standardized design, which we are doing. So the easy wins that we're working on at the minute are looking for that operational efficiency, energy efficiency linked to sustainability agenda, enhanced user experience for inmates and staff alike. You know, obviously prison is punitive, but it's also about rehabilitation as well. So we want to make sure we've got a good environment in which to make that happen. We can use it as a vehicle for data transparency, to bringing in different data sources as well, which I'll talk about a bit later. And of course, provide feedback and cost efficiency as well. And then we want to move into predictive maintenance mode, look at things like asset tracking, space, cell utilization, behavioral data, a whole raft of different things that we want to look at as we go forward with this venture with the Ministry of Justice. So to help us do that, we didn't want to do it in a silo. We wanted to bring people along for the ride and also get inputs from various stakeholders as well. So we created a special interest group, which I chair on behalf of the Ministry of Justice. And we've obviously got our core team there, which helps us deliver the digital twins. That's Kier, company I work for, which offers project management and building technologies expertise. We've got Glider, that tech partner I talked about earlier. Future Decisions, who are building physicists with a building analytics platform with many years of experience of working with live building data. And of course, we work closely with the Ministry of Justice. And then we've got a wider group of people that feed into that special interest group as well. And that's a really healthy thing and something, strategy we're kind of trying to take other government agencies on the ride for as well. And then our initial Pathfinder project was House Block C. And we wanted to be really unintrusive in our first phase. So we wanted to work with all the data streams that were available to us. This building wasn't designed to be a digital twin. So, you know, it wasn't perfect, but we had lots of good data. And the only extras that we put on the building was some some sensors on the air handling units on the roof. And I was actually up on that roof today looking at those sensors. They were quite dirty, actually. But yeah. So anyway, look at some of the analytics. Well, first of all, look at the system architecture. So we've got the building, we've got a Lorraine gateway picking up those air sensors on the air handling units. We've got the BMS, and then we've got a harvesting box, basically, which takes all that data and then takes it off site to the cloud. It goes to the Future Decisions cloud, where it's analysed First of all, it's validated and then it's analysed, and then we make a link between the live building data and that static BIM information in Glide, and that becomes our front window into the digital twin. So some of the examples of data, great, loads of dashboards, top left looking at some CHP performances. We've got air handling units in the middle, and on the middle right there, we've got some data from Fitbits, which certainly makes it wearing, because the Ministry of Justice feels like, obviously sleep in prison is complex because of noise, etc. And they think that's got an onward effect on the amount of incidents that happen the next day. So we're able to bring that data in as well and correlate it with the building performance data. But it's not really about just visualizing data, it's about driving insights and actionable insights. So our phased approach, and this is a real world application, so we can't go all power and tongs and operational prison. So we have to go in a phased approach. We kind of grow the digital twin. So phase one, we acted as a sprint to configure the system, acquire some data, do some energy baselining, which was really great, really positive. That brought up some opportunities to make some savings in the ventilation system, in the low temperature hot water system, and also in the underfloor heating system as well. And that encouraged the MOJ to invest in phase two, where we've had to put in more kit. So we've got more access to data and more control as well. And we've run their analytics again, and we're here now basically. So we're at the point now where we're making local control changes based on the analytics. And that's in quite a traditional sense, really, because what we're making is a request for operational change by basically a paper form. And that goes to the operator, and then they will update the BMS schedules based on the data, on the analytics that we've run. The savings that we're going to make, we think well in advance of our original predictions when we were in phase one. But I purposely have not moved the dial there because I'm a bit fed up with talking about predicted savings. We want to start talking about actual savings. And for us on site today, the operator, we're about to make that ventilation change based on that real data. But what we're really excited about is moving to phase three, where we do have an element of AI control. And I think there's a really exciting opportunity in the prisons because they have underfloor heating, which is obviously slow to react. And we've got ventilation systems, which is quick to react, but works very independently of the underfloor heating system. So we can bring those two things together, along with some learned building behavior AI and weather forecast. We can really optimize those systems dynamically, at the same time making sure we maintain that thermal comfort and air quality as well. So that's really exciting. We think we can make some really good savings as well. And if you think about it, we've got our primary house block there. That's getting repeated up and down the country. We could feed back into the standardized design. Do we need to do this at the same fidelity on each building? Probably not. We can get more bang per buck by really doing a thorough analysis of one house block and then taking the learnings to the others as well. So carbon savings, again, this is when we were in phase one, we made some calculations of the carbon savings. This has shifted to the right, but again, we want to be reporting on actual savings now. So I purposely have not actually changed that data at this point, but hopefully later this year, we'll start to see real data coming through, which will be really good. So, yeah, other benefits. So obviously validating the design, making sure the building's performing as it's meant to, optimizing thermal comfort and air quality, bringing in behavioural data insights. I think I'm going to cover that a bit more in a few minutes. Streamline reporting. Reporting is very traditional at this point in time. Lots of Excel spreadsheets, but we're actually streamlining that reporting. We're getting really good energy and water benchmarking, starting to move into that predictive maintenance mode. That does require working with operators really closely. We're starting to develop those relationships, and we can already see opportunities because we're monitoring everything on the network. If anything goes down, we can actually tell people about that straight away. And we've got a centralized dashboard, and then integration with FM. And, that's about automating workflows. So if something goes wrong, you can say there's a ticket in another system and go and address that rather than looking at your SFG 20 schedules, which are really expensive to maintain by. But it's also a cultural thing as well. So I was on site today at 5 Wells with members of the team from MIT and G4S, and trying to use this as an actual vehicle to kind of bridge that gap between design and build and operations. So look ahead, the MOJ, excuse me, have done some work themselves and thinking about how digital twins could, positively affect all the different functions. So they're taking it very seriously. And then we've got some more work as well. So still at 5 Wells, we're in phase 2. We're currently working on an HMP Elmley, which is a 1990s house block. Very complex because we haven't got a digital record to start with. We've got very low building intelligence, and it's a live operating prison. So lots of challenges there. And then we just completed HMP Mill site near York. And that's the first all-electric prison. So we're just doing a digital twin there as well. And yeah, basically got a gap between practical completion, where we've handed over the project, and when the first prisoner gets in. So all that hardware uplift that we require at this stage can be done in that period, which is cheaper. But of course, we want to bring that back into the design process, and that's part of the lessons learned and the governance of this project has behind it. And it will happen, and it's starting to happen already. So just looking at HMP Elmley in a bit of detail there, how do we go about that? Got a low-tech building, no digital records, fact package stuff we've got, and all the stuff's out of date. Absolutely. So to get us to a baseline, we sent someone around with a wearable scanner, created a point cloud, then from that point cloud created a model, posted that model in Glider, and then we've done some upgrades to the building to be enable us to get data off site. And that data goes to the future clouds where it's validated. Lots of complications there. We need all that semantic stuff that Dr. Stephen has been talking about, and others as well today. It's not in place, but yeah, we can basically make a marriage between live building data and that baseline model in Glider, and we've got a digital twin to some degree anyway. And then looking at behavioural data, and I think this is where it gets really interesting as well, and got a societal impact. So incidents, as you can imagine, in prison, not good for anyone, for staff, for inmates alike. And we've got a massive list of incidents that have happened in the house block that we're doing a digital twin on. Incidents come with a very high cursory price, because it's not just about the incident itself, it's about all the on-costs related to legal implications and so forth. So lots to tackle there, and the MOJ know that there's a relationship between incidents and temperature. So there's a problem with overheating in prisons, incidents in air quality, and incidents and other events as well. We can use the digital twin to correlate that data, bring it together, and with the view of trying to reduce the incidents. And then lowering FM as well. So there's a big issue with data, nuisance calls from salespeople complaining about the temperature or air quality. We can close down those calls with data where they're just nuisance. We've got all information instantly available. It's not in Lever Arch files. We've got the asset data from one place. We've got the live building data from one place. We can bring that together, which means hopefully we can go to the work site, data informed, and visit once. And if you can think about an operational prison, trying to even change a light bulb is really challenging. So, going with the right engineer, the right equipment is really a great way about going about work. And then we've got a great understanding of asset performance, which feeds into operational budgets. And then we're moving into predictive maintenance. And then it's really a good example. We're monitoring an air handling unit way in advance of an outage. A trigger point is reached, and then we can raise a work order in a system, and that could probably be a CAPM system. So yeah, another thing that we find as well is, it's not digital twin. People think about it as a platform or a software, but it takes a lot of collaboration to make it work. That it really does. So we're looking at offering these services as care. So traditional design and builders, now moving into operations, and we've got key digital twin solutions, and we've got a core team that we work with to deliver these digital twins, and we've got some specialists and consultants to help us out as well. And you know, just to say that we've got a project starting on with a school at Oak Academy, and you know, one of the things that we're looking at trialing out on Oak Academy is where we've got a bridge between the BIM data and the live building data, is to try and preempt that by using the BIM models at an early stage with the BMS engineer to then create some zones within the models, and we've got some scripting there as well, all aligned with open standards, IFC, etc., to then try and derive the endpoint naming from the BIM model from design, which would help us. Is it the right answer? Possibly not, but it will definitely put us in a better position than where we are at the minute. And then we've got a proposal for hospital building as well. So the Dyson building down in Bath is one of the first hospitals that's delivered through the new hospitals programme, and we've got a great foundation there in terms of data, in terms of building intelligence to do a similar pathfinder, which will hopefully inform the new hospitals programme. And we're also working on other ventures related to our capital projects as well. So anyway, bit of a whirlwind tour, and thanks for listening.
Our last speaker is Rui Tan. Rui is one of the members of the SBD team. So he's one of the lecturers in the MSc in Smart Buildings and Digital Engineering. So many of you know him. Prior to UCL, he was also at Lawrence Berkeley National Laboratory. And today he's going to talk about some of his research, which is AI-assisted control optimization, and looking at demand flexibility, which is your expertise, one of the many. Thank you, Rui.
Hello, everyone, and thanks for Valentina's introduction. And today I will share a recent work about AI-assisted control optimization for demand flexibility aggregation across buildings. So just quickly walk through, I think all of you are very familiar with the background of buildings, the role played in the context of energy use and the carbon emissions. So in general, 1/3 of energy go for buildings, and especially for operational stage, 28% of carbon emission comes from our buildings. So this emphasizes the importance why we focus a lot on building operation and the control optimization. In addition to that, so we are facing this global climate change. So on the demand side, we want to electrify building systems. So this will increase the demand of buildings. And on the supply side, so we want to, for energy system and the power grid, we want to absorb more and more renewable energy resources. So the problems for this kind of renewable energy resources are intermittent. So this will cause a lot of uncertainties introduced in the power grid and system. So this is the reason why we need to consider energy flexibility to accommodate these uncertainties and the challenges in the low carbon energy systems. So just an example here, a figure is based on estimation. If we introduce flexibility in energy system in UK, so around 17 billion pounds can be saved annually. So if you see the left corner of this dark curve, so it's another typical example. So the electrical demand in a building within a day is very imbalanced. At least it's not like what we expect for buildings to consume electric demand. So in this case, control algorithms is like a brain for buildings, not only for demand flexibility, but also for energy efficiency. So for all the control algorithms, basically we can separate into three types. The first one is rule-based control, so which is currently widely applied in reality. The second one and the third one, model predictive control and reinforcement learning. So basically are two more advanced control algorithms. So because demand flexibility, the essence is to optimize the building system. So the key point is the optimization process. So this optimization process cannot be realized effectively through a rule-based control method. So this is the reason why also Stephen mentioned a lot. So why we want to invest a lot of efforts on model predictive control and reinforcement learning. So in general, model predictive control, the logic is we base on a model to predict the future, and we base on this prediction to decide how to operate our buildings. And reinforcement learning is quite different from model predictive control. It's basically model free. It's based on the interaction between the control agent and the environment. There are a lot of successful applications and impactful cases using reinforcement learning. In general, reinforcement learning is a type of machine learning method for decision-making process. So it's the same process for the control optimization in buildings. So for control optimization in buildings, it's another kind of decision-making process. So this is the reason why it is possible to apply reinforcement learning in building controls. So if you see the left-hand side, so this is the basic structure of reinforcement learning. Two key elements. So one is the agent. So agent is our control algorithms we want to focus on. The environment basically is the agent. So where to learn and develop the control logic. So because reinforcement learning brings the concept of environment in front of people realize the importance of reinforcement learning environment. It's not only about train outperform reinforcement learning algorithms. It's also about benchmarking the control algorithms, because we have a lot of different control algorithms, rule-based, model predictive control, reinforcement learning. So if you are facing a specific case study, most likely you don't know which one is outperformed. So this table basically listed all the current existing environment for single buildings. I think the last one is the Bob test. I think Stephen mentioned. So this is, I think this is the most popularly platform or environment for train control algorithms in buildings. So in general, all these platforms basically are focused on single buildings. In other words, for single building environment, current literature has been well developed. But the situation is quite different for aggregation of demand flexibility. So that is multiple building levels. Few available environment in the literature. So basically, here are three main environments. The last one, the CityLearn, I think also is which one is most popularly among these three. The commonality across these three environments is they are using simplified model. But for simplified model, normally two ways. One is through RC model, so this gray box or hybrid model. The second one is purely based on data, so data-driven model. The problem of this simplified model, one is especially for data-driven model. So when you have input output determined, everything in the middle, in the middle is black. It's black. So there are lack of intermediate variable checking, and as a result, the result is lack interpretable and incapable of capturing full building dynamics. So another reason is this kind of simplified models are constructed for very specific scenario, which make this platform basically are not suitable for benchmarking. Because for benchmarking, we want to accommodate the scenario as much as possible. So in summary, the overall situation for multiple building demand flexibility or demand flexibility aggregation, a white box model basically can provide the highest fidelity and physical reality. But problem is that this kind of model is underdeveloped for multiple building scenarios. So to solve this problem, a platform has been developed by PhD student. So I work with the PhD student to develop this model. So in general, if you see the right-hand side, three parts for the platform in this structure. The top one is a standardized interface using OpenAIG. The main advantage of this OpenAI regime, so basically we can implement all control algorithms, including rule-based, model predictive control, and reinforcement learning. So the bottom layer is the physical energy system. So in this case, or in this presentation, so I won't touch on this active system. So I mainly introduce these building models. So here we use white box model of N+. So in the middle part, the problem is that how to communicate between the interface on the top and the physical energy system. We wanna, because control system most of the time require this real-time communication. So if you see the left corner, so basically we walk through the literature and summarize all the methods for the communication between different models, not only for building control, but also for the general areas. Basically, there are three types of communication or real-time communication. So the first one is this one-to-one communication. So the problem is for this type of communication is very restrictive. So this N+ Python interface is one example. So it's not that extendable. The second way is through a middleware. And I think one typical example is BCVTB, building control virtual testbed, so which was developed many years ago by Lawrence Berkeley Lab. And now I think it has been stopped to update. So the problem for this kind of middleware method, there are a lot of update compatibility issues. So the last one is the mostly applied for this kind of communication across different models, different programs, and different software. It's called functional mockup interface. So it's a standardized protocol. So basically, to enable this communication method. So in this case, we apply this functional mockup interface, this kind of a standardized protocol to realize this real-time communication between physical layer, white box model layer, and control agent. So the standardized interface to implement your control algorithms. So we convert the building stock, so macro buildings, into FMU stocks. So basically, we coordinate these different FMU stocks to realize this macro building coordination in this case. So this is the general logic for the platform. To demonstrate the functionality of the platform, so I just present a simple case study. Here, 4 buildings, in this case, 2 small office building, 2 medium office building with different electric load profiles. Another advantage of this platform is that for demand flexibility aggregation, so most of work currently are focused on the control focused on building level in the context of aggregated building demand flexibility. And for this platform, because we apply this physical white box model, so we can realize the zone level or control optimization for the coordination of buildings. Our control objective in this case, so if you see the red circle, so this is the aggregated load profile of these four buildings. And our control objective here is to reduce the load profile in this red circle below the red line. So red line is the threshold. So we want to implement this peak demand limiting. And meanwhile, we want to minimize the energy use of these all 4 buildings, as well as maintain the indoor air temperature within acceptable range. As I mentioned, so the control at the zone level rather than individual building level. So this is one example of a small office. The system here is this is the floor plan for small office building, 5 zones, and the control variables here. The temperature, indoor temperature set points of individual zones, as well as the supply air temperature. So 5 control variables for small office building, and 6 control variables for each medium office building. regarding the selection of algorithms of reinforcement learning, here we select soft actor critic, so which is a very standing out algorithms in the domain of reinforcement learning. So reason is the objective function is different from also reinforcement learning. So because this method has more capability to avoid local optimal in control optimization. The second one is this algorithm is very fit for the aggregation of demand flexibility, because when the number of buildings is scaling up, the problem become high dimensional. And this method is very suitable to solve this high dimensional task within the domain of reinforcement learning. In this case, we want to reduce the peak demand or shift the load only through the thermal mass, the passive storage. So we don't consider any active system like battery, PV, this kind of stuff. And also in the current available method, it is not that easy to use thermal mass of individual buildings to realize the coordination of demand flexibilities. So you can see here four figures for different buildings, to small office to medium office. So we can use the top one, the small office building, as an example. The normal condition, the two yellow vertical line is the normal period, so the baseline. So this is office hour. Non-office hour, the air conditioning system, cooling system will be off, and this is the normal case. But you see, if because we want to reduce or shift the load, so the control agent can provide the pre-cooling before office hour, and afterwards the temperature set point is slightly increasing. This problem is challenging because if we have a higher temperature, we can minimize the energy use, because higher temperature, lower cooling demand. So that means minimize the energy use. But problem is that if we have a higher temperature, the cooling stored in thermal mass will be over-released. So that means the cooling to be supplemented in the green zone. So that is the peak demand event. So will be insufficient. But if you have a lower temperature, you will have a higher energy use, but the cooling stored in building thermal mass will be over sufficient for your peak demand limiting. So you need to find out a proper level of temperature set point in this case. So through control agent of this reinforcement learning, so the control accuracy is very high. So this kind of control accuracy, I think, is totally beyond the human capability. So if we only based on human domain knowledge, so we cannot realize this kind of accuracy of control optimization. So this kind of message is beyond of our testing on the platform. Here, another follow-up result. So the baseline, the aggregated electric demand. So you see the baseline, and after this control optimization and coordination of thermal mass across different buildings, so we can see the load profile can be ensured below the threshold. And meanwhile, so if you see this figure, we don't consume actual energy in this case. So because even though we consume actual energy for the pre-cooling time, but we control our temperature at an appropriate level to ensure we consume minimum energy use in this case. So in general, this is the overall result. And all these kind of codes platform will be open source in GitHub. So now we are doing a last run to further check and put some explains on the code. And the last slide is about future work. So the first one is, as I mentioned, the aggregation of demand flexibility is a high dimensional task. So we need to apply this multi-agent system basically to separate very complicated tasks into subtasks. and we can apply this distributed method to realize this kind of optimization. And second one is extract the rule from reinforcement learning. So because this interpretability is very important for control optimization, people need to know what happened for the whole optimization process. So we want to extract the rule. It's not only about extract the rule in understandable manner. It's also about we want to apply this natural language model. So basically to extract the rule through this natural language way to make everything more straightforward. So the last part is about this active system. So as I mentioned, all this kind of stuff are only use thermal maps of buildings, and later, so we will introduce PV system, EV system, as well as storage system. I think that's all my presentation.
Thank you, Rui. Yes, only one because we need to go.
Yeah, we can go back to the graph that's got the 4 offices showing the pre-call period. So from what I'm saying, it's basically showing you've got a coinciding pre-call for all the buildings. So I think effectively, you're sort of putting out in a way an obvious thing that you've got a coinciding peak. They're all pre-cooling at the same time. And obviously we're well aware that with AI, sorts of data centers, having to ask the same question. This might be what you mean by rule extraction, because in a way, as an engineer, it's kind of obvious you're going to have this peak at pre-call. And I kind of imagine what you were doing in things like Guide 36 work. Is it plausible you say, well, for the greater good, you can adopt a control algorithm that by default squashes that peak, uses thermal mass, uses night purging. Many buildings that they can use night purging. So do you think, in terms of not having to completely run that engine, the fundamental principle is trying to squash your peak? Do you think it's plausible to sort of feed back with a greater good, starting control algorithms for buildings that will fundamentally reduce the likelihood of coinciding peaks anyhow? Does that make sense?
Yeah, so the first one is this peak demand limiting is one example. So basically, this peak demand limiting is one focus of this demand response or demand side management. And one point here, we have this coinciding, this kind of stuff. We just want to test the functionality of the platform. And second one is, so if we want to avoid this kind of coinciding phenomenon, so you can definitely impose a constraint or penalty in your whole optimization framework to avoid this phenomenon. So in general, this white box model basically provides you sufficient freedom to implement what you want to implement in the platform. So basically, it depends on what you need. Here is just an example. So it doesn't mean, so basically on this kind of phenomenon can be a result through the platform. Thank you.
Thank you. Thank you for this. Thank you, speakers, and thank you.